It started recording now.
So, Tim, don't be worried about Chima's mathematics. This chapter is really to help you get ready to understand the basics of models. And if you look at the questions at the end, Priyansu is sick, but if you look at the questions at the end, you should be able to understand what's a stochastic gradient. You know, when you're starting to look through a model and there's something like epochs, what's that? What's a learning rate? How do you interpret your curve to show that you're not overfitting or underfitting, or do you need to adjust the learning rate? And you know, when you're sort of thinking about the distribution of your data, how does that go? And so really, so don't get so bogged down with math. Seriously, I think it's important, but like don't get discouraged. And so yeah, Chima.
Okay. Yes. So I will share my screen. It's the entire desktop. So I made some slides. Where is it? I made some slides. So hi, Jeffrey. My name is Chima. I'm a Georgia Tech computer science student. One thing I always say is I'm really excited to be in the study group, and I like being in the lab. Nice. So this chapter is pretty much focused on training models, sort of like getting the dev, like we're going to take the deep dive into some of the stuff we've sort of almost taken for granted. So I'll start. Can you guys see the presentation?
Yes, I can.
Yeah, we can see it.
Yeah.
So just sort of like a precursor. So just sort of, this is what we're trying to do. This is what the chapter is trying to do. In the past, this is how we ran ML models. We'll call it from the library, then we'll say, okay, fit your label, fit with your data, basically. But more, yeah, like he said, what she does like black box. We didn't really bother too much inside, but not anymore. So we're actually going to try and go inside. And he gave some reasons you should care. It's sort of like, it'll help you pick, if you know what's going on inside models, you'll know which type of model to pick based off your data set. And it'll also help you to debug, so that if you're like using one of the models from Skit library and it's not doing how you want it to do, you can be like, oh, I think this is why. Yeah. So we start off with linear regression with one variable. And the goal was to predict a single output value from a single input X. So pretty much given an input, we'll compute the output using our weighted sums. Now the weighted sum is what we're actually trying to do. And then we're also trying to identify the bias term. And from the previous chapter, we know there's an example of a supervised learning algorithm. So this is sort of like the hypothesis, sort of like the, what do you call it, our guess. And because it's since it's with one variable, we're only predicting it with one feature or one X value or one thing in the X value here. And then these are the weights. So like this our mission is sort of like to find, our goal is to sort of find the values of theta 0 and theta 1. Right. I think we covered this much so far. We covered this much last time. And then sort of like, there's an example where we had, I noticed this from classes, was just sort of like the test average goes hand in hand with the approval rating of the teacher. And the higher the test average, the higher the approval rating for the teacher. And this is just data. Now what we're trying to answer is questions like, if the teacher rating, if we know the test average, how can we get the approval rating? So there's two ways to form the linear regression. There's two ways to make it. There's two ways to get these values of theta. These values of theta. This is also very similar to the form y is equal to mx plus c, where theta 1 is the gradient and theta 2 is theta 0 is the y-intercept. The normal equation is one thing I didn't like that he did was sort of just dove into the normal equation, but I feel like before you get it, you have to sort of understand the vectorized form of the normal equation. The vectorized form in terms of how to represent this data in vectors form. So I tried that. So from the previous example, basically we're trying to get this equation right here. Y hat, or our prediction, is equal to theta times x. That's the short form. That's the more concise form. Now the x, this x here, the x here, where is it? This x here, we get it from, this is our original values, 0, 1, 2, 3. Then we append a column of ones. We add a column of ones to it. And let's say our theta values were this. Then our y, which is this x, we'll just multiply. We'll just do matrix multiplication to get our y values. Does this portion make sense?
Yes.
Okay. So with the normal equation, we just directly compute the values of theta, as in we'll get this, we'll get this, we'll get this one. Once we do this, very funny.
I have a question for you, Chima, that I think may be helpful.
Yeah.
Is why are we adding ones? And it's and I think it's something about understanding matrix multiplication, right? With the dimensions, right? So what's x? Is that a 2 by
2, so
2 by 4 or
no, 4 by 2, my bad, 4 by 2.
4 by 2 matrix, right? And then the theta is a 1 by,
2 by,
because 2 by 1, because if you have a 4 by 2 matrix, then the next thing you multiply it by has to have a 2, right? That's why sometimes you have to transpose the matrices,
yes,
right?
yes, that's exactly. So did you guys catch what Judy was saying?
Yep.
Okay, nice. Yes. So if you notice, it's just sort of like this represents, this portion right here is just sort of one column. This one didn't come with it. This one didn't come with it. And they'll put the x, they'll put something like x1 and x0 usually on top of these ones, which is representing this feature. And then x0, which he says here, x0 is always equal to 1. This x0 he's talking about is these columns of ones. He said those are always. This is more of the general, this is beyond if you have more than one x1 here. This is for the general case.
And also, could it be to get the bias term with adding that?
Yes, exactly. That's why, because in this equation is theta 0 times 1. It's theta 0 times 1. So in this place, we're explicitly saying, okay, theta 0 is 1. But yeah, so after we do the math, we just get this vector back here. We just get back this vector right here after we do this really funny math. Yeah. And this is where he did it in Python. This is the part where he did it in Python. I just wanted to catch and note that this line, the first line he does here, he's adding a column of ones. So in this example, there were 100 examples. There were 100 training examples. So he added columns of ones to the x to come to catch that. So there are also some problems with the normal equation. One, it won't work if x is not invertible, or pretty much if you can't get this inverse right here. And it also doesn't scale well with large data sets. The bigger the data set, the more difficult it becomes. Now, normal equation is one way. The other way is sort of like using gradient descent. But before that too, we should also talk about the cost function, MSE square error. This is the equation for the MSE square error. It's pretty much the difference between our predicted value and our actual value y. Let me see. So I just used, like, say for our previous example, these are our x values, 0, 1, 2, 3, 4. And let's say we say our theta 0 is 2 and our theta 1 is 2. And we want to compute the cost. So the cost is not a vector, it's a value. It's one particular value. What we do is we compute this one. We just basically 2 times 0 plus that and compute. These are all our predicted value, right? These are what we're saying the values of y should be. But these are the actual values of y. So we'll find the difference, square it, and then take the sum and then the mean. That's why it's called mean square sum, mean square error, because we do mean, square, and then before we get the error.
Could you pause there, Chima? So just to try and shorten the learning curve for Jeffrey. Now, with machine learning, you have, so what we're doing now is supervised learning. And supervised learning means you have your input data and a prediction. When we're thinking about this linear regression, we're talking about, you have to always think about numbers. So for example, you could be predicting housing values, you could be predicting total bilirubin values, you could be predicting something like GFR, glomerular filtration rate. So when you're doing those numbers or age, then that's a simple prediction model that requires linear regression. When you're using one value and the distribution is linear, then it's linear regression. Now, so the model works by penalizing it based on when it makes the wrong assumption. And so what that means is that if this example that Chima is showing, like the prediction is 2, but our actual value is supposed to be 4, then you need to find a way to keep telling the model, bad model, you did not do a good job, and so that's the cost function. And so always when you're hearing machine learning, you'll be hearing me trying to minimize this cost function. But at the end, how do we know that our model is doing well? When it's these numeric values, then what we use is the MSC, which Chima has done a fantastic job of showing here, mean square error, or the root mean square error, or the mean absolute MAE, something, average or something.
Yeah.
And so those are the metrics we use. So don't worry too much about the math, but you should be able to listen in on the lab meeting. I think this week, Imon talked about cross-validation and initializing weights. And that, I said, should be something that all of us understand because you know that that's what you should be doing. And so go ahead, Chima, but this is fantastic. Your approach right now is very good.
Thank you. So
Yeah, thanks for explaining.
no problem.
Chima, I want to also add something before the gradient descent. First of all, like this is fantastic, like in the way that you created these slides. I'm so impressed. And one other thing, so
and who are you, Elmira? You have to introduce yourself.
Yeah, sure. First of all, let's see. Welcome, Jeffrey. I'm Elmira. I'm a PGY5 radiology resident at University of Illinois. And so I approached Judy because I was interested in machine learning, and she was kind enough to add me to this group. So I'm mostly trying to learn how to do signal processing, but these are the basics of machine learning that I think it's very important for whoever wants to do machine learning to learn. So that's why I find this group very, very helpful. So I'm very happy to be here and welcome.
Nice to meet you. Thanks.
Thanks. All right, so that's that. So Chima told that how can we solve that optimization problem? How can we decrease the cost using the normal equation, as he saw that equation before. But apparently by default, scikit-learn tool doesn't use that normalized function. Instead, it used something called a singular value decomposition, and he abbreviated to SVD. So just to keep that in mind, so scikit-learn doesn't use normalized equation. It has like a different thing. It uses pseudo inversion of the matrix. So yeah, that's one other thing before the gradient descent.
Yeah, no, you're right. You're right. It uses because of the problem, because of this problem that of finding non-invertible. Basically, this portion we're trying to find the inverse of everything in here, and that might not always be possible. Depending on your x values, it might not always be possible. If two of your, it's a little too, okay, there's a problem in linear algebra where it's like if any of the features are dependent on each other. Like if you have square, like say you have square size, like say you have the size of a house and the size of a house squared, it won't be invertible. As two features, it won't be invertible. Yeah, so they use that to sort of make the pseudo inverse. Yeah. But let me see. Yeah. Okay. Yeah. So I also wanted to point out I chose those values on purpose because if you look at the 8 value, right? Imagine if we got everything sort of like the 8, where the predicted value and the actual value are the same. The difference would be 0. The square would be 0. Now imagine that for all of them, right? That's our goal. That's what we're trying to go. In which case the cost function will be 0 or something very small, something close to 0, because sometimes we can't get it every time, but something close to 0. Yeah. So this is just sort of like the meme thing was just, I like this. So the general idea of gradient descent was to, so you start with random values of theta, right? Start random values of theta 0 and theta 1. And then we gradually adjust those values, right? Till the cost function is minimum. Those are sort of like the 2 high-level view of gradient descent. This is gradient descent on the whole.
Can I, yes, go ahead. This, I see it on the next slide. So
Okay.
the gradient descent is, remember, you're never going to train your algorithm one time and get the perfect, unless you're overfitting your data, right? You're never going to train your algorithm to be perfect the first time. It requires a lot of iterations, right? So if that's the case, the algorithm that tracks how many times you're going, what parameters you're choosing, until you get to the minimum is the gradient descent.
So he gives this analogy, like imagine you're on the top of a hill and your house is at the bottom. So imagine I'm here and then my house is at the bottom and I'm trying to go from here to here. I can't see, why not? So there's a thick fog. And then what I do is I start feeling my feet. I feel like this is probably something we can relate to because if you're on that incline, you sort of know where it's steep and you just sort of like go towards in that direction. So that's how gradient descent is. So if you plot the cost and the value of theta that you're choosing, it will always sort of come with this bowl shape. That's why the analogy for the hill, thus the analogy for the hill. I can post a video in terms of why this is always so. I have a video in the link, but we can watch that later. Sort of like why this is always so. And then we start off with some random of theta. So if we start off with random value of theta, obviously our cost, this will be high because this will be high because the differences will be very much because we have a lot of differences. So those will be high. Thus the cost will be high. And once the cost is high, again, we start off here and we're trying to go here and make it as close to 0 as possible. See, this one doesn't actually get to 0, but we can get it as close to 0 as possible. That's pretty much how gradient descent is trying to do. And for it to work, we need to tell it how large steps to take as it's going down the bowl. And this is sort of like, we tell this by giving it the learning rate. And then the other one is how many steps to take. Those are given by a number of iterations. So you can tell it either to, okay, only move baby steps and be very, very careful as you're going down. In which case, the learning rate, this is what it'll take us some time. It'll be going down, but it'll take some time before it goes to before it reaches the bottom of the bowl, right? And then, but if your learning rate is too high, imagine sort of like you're a hyperactive child and you're jumping over the bowl, right? Imagine like, or I had superpower and I was just taking very large steps. You would somewhat miss the bottom, which is depicted here. So far, does everything make sense?
It does.
Okay. Yes, so this is the actual content. This is the actual formulas for gradient descent. We initialize the random values for theta 0 and theta 1, and then we repeat for number of iterations, which we tell it how many steps to take. Take this large steps, right, and reduce it. Take this large steps and reduce it by that amount. This is gotten from, so let me explain this one just a little bit. So this is the predicted value. Anytime you see theta x or x theta or some form of that is the predicted value. These are the values we are saying that should be the y value. And then the model is like, okay, this is the actual y value, right? And then we'll multiply, and then we just sort of, oh yeah, this is the gradient. This is the formula for the gradient. My bad, this is the formula for the gradient. In this formula, for our theta 0, j will be 0, and theta 1, j will be 1. This is how, yeah, this is how he sort of applied it in Python. You can see the random initialization of theta right here. And then just again for this, yeah, this is pretty much just a repeat of the previous line. Okay, now gradient descent, there are three main
Quick question, sorry,
yeah.
before you move on. Just so I make sure I understand all these, I'm just kind of struggling with the, by the way, hi Jeff, I'm one of your classmates, Sina. So gradient is basically, so so if it's negative or positive or the size of it, it's just to make sure I understand it correctly, is to tell you how, like the direction that you need to go and how far away you are from the minimum, right? When you're calculating the gradient, that's what it's telling you. If it's negative, like you're that way, right? Right. So that's,
Yeah.
Is that what we're doing? Okay.
Yeah.
So imagine, Senna, you're on top of it. You're going to climb Mount Kilimanjaro, okay? And you're like, man, I need to figure out what's the most efficient way to climb there. And we've had 1,000 people before you who've mapped out all their routes that they've gone down, okay? So you have the hill and you have the bottom. The bottom could be your house or anything. So you have to have direction, right? Because you cannot keep, if you're going up, you're going away from the way you target, and then the steps, the direction that you're gonna take. And then after that, so you keep iterating. Now, if the first round, the person took you through lions, you'd be like, bad model, I'm gonna be eaten. So you penalize. And so the cost function there is very big, right? Then you go back on top of the hill. And so every time you do the iterations, that's the epochs, right? Every time you have to go back and start the training again. But the training steps, the learning rate is how many steps you're going down the hill to get it. So the gradient descent really, gets you the direction and holds the parameters to try and get to a minimum.
Thank you.
I don't know, I didn't say this part, but these two are hyperparameters, as in you pick them. With experience, it becomes, you can pretty much pick these ones very easily. These two are hyperparameters. Thus, he's warning you that if you select the learning rate as too small, this is what will happen. If you select the learning rate as too high, this is what will happen. But we don't typically have a problem with number of iterations, right? Because once we just notice, like, let's say you keep getting 0.1, 0.2, and 0.1, 0.2 as like your cost, you can just tell it, okay, this is small enough. Stop iterating. Stop going. Stop doing that. Like, pretty much. So that's why we don't typically have beef with the number of iterations, but there are some problems with that one, like we described. This map, we don't really typically need to worry too much about it. It's just sort of like this is the part that the general gist of it, that you're reducing that. So with gradient descent, there's 3 types. There is batch, there's stochastic, and then there's mini batch. So I want to talk about batch and stochastic gradient descent. So in the formula here, this formula here, right? We see we're iterating from M represents the total number of examples, right? So if we have 5 examples, M will be 5. We will do this 5 times. If we have, it's very similar to the cost function. So this one right here is very similar. This one just means we sum it over here like we did here, and we get the total. So in this example, there were 4, so it took the form of all 4 of them. But as it becomes larger, like say, like 200, M will become 200. Now with batch gradient descent, what we do is we'll compute that sum, right, over the entire data set. So if we have 200, we'll compute the sum over 200 data sets. If we have 3 million, we'll compute the sum over 3 million data sets, like in total 3 million data sets. And as you can tell, yeah, this definitely becomes slow with the larger data sets. Again, to move one step, as in to adjust data, right? These 2 things will need to compute much bigger. Like for the 3 million, this will really hit you. For 3 million, it'll become too slow. So then you can also do, if you don't want to do that, or if it's taking too long to do that, and what you can just do is use stochastic gradient descent. And stochastic, I found out last week, means random. So we just pick one random value out of our entire training set. So if we have 3 million, rather than moving, adjusting data using just 3 million, we'll just use one value. We'll just use one example for the X here. And this is what happens. Now, although it's faster, right? It doesn't really pinpoint to the specific minimum. It just sort of hovers around and goes around the minimum and doesn't really settle down. So it's sort of like a tug between the speed and how smooth you're getting your value. Now, this is stochastic gradient descent. This slide is sort of like the theme of the entire chapter. It's sort of like, okay, this is what we normally write, right? This is what we normally do. Like in the previous chapters, we'll use this library, skitlearn, which has our model implemented. And then we say, just run it, give it the total variables. These are the hyperparameters, the iterations, number of times, where's the other one? The alpha, as in the learning rate, the rate here. These 2 are the basics. TOL, I think, is the acceptable difference between, I can't remember what it stands for, but it's sort of like
Tolerance.
Yeah, the tolerance. Sort of like if you get your values between these values, that you should stop iterating. So people have designed this. People sat down and designed all of this into this for us, making it so much easier to write. But if you didn't want to use this, then you just do all of this on your own. Yeah. Does it make sense so far?
Yes, and Chima, I am very, very impressed with your presentation.
Thank you.
So one thing is that you said that the stochastic gradient descent never really stops, right? So that's why you're going to tell us in a few slides about early stopping, and also why you need to have that tolerance, else you'll never come to your minimum, to your bottom of the hill. You're just going to jump around.
Mm-hmm. Yes. Okay. So mini batch gradient descent, rather than use, okay, so these two are extremes. You use either all the 3 million or you use either one. Mini batch is like, okay, let's find some leeway between. And it sort of uses the, I think he runs code on it. On mini batch gradient descent. It sort of uses like some of the data set. It doesn't use either all of it or some. It uses some of the data sets. Whereas, oh no, it doesn't run the code on that one. Okay. This one is, so because of that, it's sort of like it acts in between. It has some, it's random like stochastic, but to a lesser degree. But it still walks around the, but it's not like it doesn't, it's more smooth. It's also somewhat smooth like the like the batch gradient descent one. Let me see. I think, no, this always happens. Oh shoot, this always happens. I wanted to show, this is actually an animation. This was actually an animation, sort of like showing you how you can get, but Binder crashed. I'll get that one after. Does it make sense so far?
Yes.
Okay. And as you can see, with both gradient descent and the normal equation, we're predicting our values of theta. Here he represents it as an array. The first one is theta 0. The second one is your value for theta 1. Similarly, in the normal equation, this is what we look like when we just computed it real quick. We get the theta 0, theta 1. Okay, this is where I had somewhat beef with him. Well, sort of, he just jumped into this one. But okay. So the first one we've been doing so far is with one value of x. We only had one feature. Where's that equation? We only had one of these x's to deal with. We only had one feature. So, but say I added more like this one. Like, this is what will happen. Now, the reason why everything's vectorized is because it makes it very consistent. Like a lot of stuff is very consistent once it's vectorized. I'll explain why. So like say I added a new feature. This is x1, this is x2. And we're trying to get the teacher approval rating based off the based off two things, not just one anymore. Right? Not just one anymore. This will be, it's still, if you notice, the equation didn't change. The equation didn't change. Y is still theta x, right? But what we now did is we did, is that a 0? Oh, my handwriting is bad. That was a 0, so we just put this here. This is, just did this. This is now our total x thing. This is all our x, right? This represents the first column, column 1, x1. This represents the second column, column 2. And then we also concatenate our values, our ones, like we did before. And this is how we'll get the y. I didn't do the math. I think I timed out on the math for this one. Does this part make sense? Does this slide make sense?
Yeah, I have a question.
Yeah.
So my name is Toby. I'm a research intern at HITI. Based on this matrix multiplication, what I understand is when you're multiplying two matrices together, the column of the first should be equal to the row on the second. So 3/4 multiplied by this has 3 columns, this has 2 rows. So I don't know how it can be multiplied together.
1 by 3. How did I last one. I think I probably made a mistake.
I also noticed it here, so I was trying to wrap my head around.
This is 1 by 2. The other one is 1 by 3. This is 1 by 3. I think
I
I
didn't
said
spend too much time on this, but sometimes you have transpose before you multiply.
that's my bad. I see what you mean. I see what you mean, baby. I see what you mean.
Yeah.
I should have just flipped it. I get
And
what
Chima, one question. Are you trying to get at polynomial regression with those x1 and x2s?
Yeah.
Because of what my understanding was, like x1, first of all, I thought that you can just fit all of your features in x vector, like all the different elements of the your data can be all summarized in x vector, and you can just use it as your in like linear regression, multi-class linear regression. No, not multi-class actually, multi-variable linear regression, but polynomial regression to me looked like if you or actually your data is not linear. Your data is just it has like not a line function, but like a polynomial function. Like it has squares, or like y is equal to that thing. So that is like not a linear function. So polynomial regression to me, it felt like basically we're defining our y function not as a x theta, but something different with some squares and like some polynomial features to it.
I see what you mean.
Fit our data.
I see what you mean. Basically, we're using a new. It's not linear anymore.
Correct.
Yeah, it's not linear anymore. Yeah. I get what you mean. Yes, you're right. That's right. But I felt like I added this one. I was my bad. I was coming back to this one. I added this one because of this. He keeps referring to some general stuff, to general equations. Sometimes he'll refer to general equations, but which I felt were. I think there was a portion before that I saw this. That was why I included it in the slides. But no, you're absolutely right. In polynomial regression is where we're using this one. It's slightly different from linear regression. Yeah.
And that just means that if you look at the polynomial equation, you cannot draw one straight line into it, right?
Yes.
That will match all the points, right? So you draw like something like a U-curve through it.
Yeah. No, that's right. You can't draw one straight line through here, because then what are all these ones? So, but you can draw, if you draw the nice little curve, should work. But yes. So pretty much with, like I was saying, just recognize either this one or theta one. Usually everything here will just be summarized. The normal equation, like I said, is still the same with, even if you have more than one feature. Normal equation is still the same. The only thing that changes is the, sort of like with gradient descent, you'd have to do this. Usually sometimes they summarize this as this thing right here. Where's they summarize that? I saw that equation before. Yes, they'll summarize everything. So anytime he bolds something, that means it's a vector. I wasn't sure if everyone caught that. So when he bolds something, he says it in the beginning, it means the vector. So this vector of theta right here means all of these. And this one, and as you can see, this is our learning rate, and then gradient. Yes, this portion makes sense so far.
Yes, it does.
Yeah, I liked the checkpoints we were doing last time, just sort of like check if everyone understood. Yes. Does anyone need me to go over any specific parts? Let me see. Okay.
This summary of the last week, that was great. Awesome.
Yeah, I realized I needed help with that one. That was helpful. Okay. So learning curves. Nice, 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 nice. This one. So one of two bad things can happen when you train. So originally, these values that you're given, these ones that you're given, these are your training. Like I think we're at this point, we usually have, okay, so for Jeffrey, you're given an entire data set. I think like Judy said. And then you normally split it, what did I do? You normally split it between your training and your testing data. You normally split between your training and your testing data, right? They're giving you an entire data set and you split between your training and your testing data. And you basically run all the models, like your linear regression model first on your training data, and then which is the data your model can see, and then you apply it to the one it cannot see, right? And your goal is to reduce the cost function, that original cost function, right, on this data that it hasn't seen, right? This is how you know it's a good model. Yes. So just a preface. I'm gonna summarize my shit. What happened? Oh yeah, she's not.
Maybe you just lost your window.
Oh. Yeah, I think I'm trying to get. Oh yeah, she's back. She's come back.
Yeah.
Nice. Okay. So one of two. So he points out one of two bad things can happen after you get your theta values. Either it works really well, like super really well on the training data, right? Which is the one it's seen this. I've seen the imagine like a practice test and a test. I've seen the answer. This is something I'm very faulty of doing. If a professor gives a practice test and a test, because I know I can do really well on the practice test, right? And then I bomb the test, which happens. That just means like, okay, instead of me, that means I pretty much I was like, I learned the pattern in the practice test, but I'm not able to generalize it to the actual test, right? And when that happens, this happens with like your learning model, where it does really well on the training set, but it does poorly with the test set. And when that happens, it's called overfitting. And we say that the model has high variance, right? Then there's the other case where I can do very poorly on the practice test and very poorly on the actual test. In which case, I'll say this is underfitting. The model is not really good, and it will say it has a very high bias. Are these distinctions, does everyone catch the two distinctions? The practice test is sort of like my training data. This is stuff I have access to. And the actual test is sort of like the test is representative of my testing data. Now, we usually use the learning curves as a way to visually spot these problems. Now, whenever you plot the size of your training data, the training set size and the error, or the cost function, and you get something like this. Again, we want it to be low. We want both of these graphs to sort of like be low down here. Yeah. And both of them suck, which means that they're scoring very poorly here, right? Since both methods have errors above, you should some people will just plot this graph. And once you see this graph, you should be able to tell, okay, this looks like it has high bias, right? And this one, on the other hand, this is like it has high variance because there's a gap, there's a huge gap between, it seems to be doing, the training error is below the desired performance, as in it's doing very well, right? And the testing error is way above it, which means I'm doing well on my practice test because I've seen all the answers, but I'm not doing well on the actual tests. Does the distinction make sense?
Yes, the left-sided one is underfitting and like it's performing terrible in both of them, and the right-sided one is overfitting, meaning that your example was great, meaning that you're doing perfect in whatever the teacher gave you before, but then you can't generalize it to the validation part.
And that's what he was trying. It's not as apparent. It's not like, it's not really as visible in the plots he was giving. In these one, in this plot and this one, you can't really like see the actual trend that you're.
Yeah, the fact that you added that desired performance is perfect addition to that. Perfect.
Yeah. Yes. And then, so with that, then he also talks about the bias variance trade-off. Now, if your model sucks, like let's say for in my case, I'm trying to learn how to study for this test. If the model, if the approach is very complex, like if it's too detailed and too specific for the test, then we're going to have this problem. Then we'll get into the problem of like overstudying towards the practice test, right? If we put too much into it. Whereas if we don't, then we get into this problem, right? Yeah. So just talking about model complexity, like if you use more complex, like he gave this example using this specific polynomial. Like the green one is it passes through almost all of his training set, right? Passes through almost all of them. It's very complex versus the red one that's super simple and low-key's like not as smart as it passes through some of the training set. That's what he was trying to do with this one. Yeah. And of course, I Googled the mean for it. That's not a plus. So if this problem, this one is somewhat easy to fix. It's relatively easy. Just make it more complicated, like increase the complexity. But what do you now do if, let's say, I'm doing very well on the other one? That's what we're trying to do here with the regularized. He talks about regularization. That's where he talks about regularization. There's three main parts. There's three main types of regularization that he talks about. Ridge regression, lasso regression, elastic net. Wow. There's probably more, but this is the main thing with the regularization. Nothing really changes except that cost function is no longer our mean squared error, right? It's no longer like our mean squared error that we knew before. It's mean squared error plus something. Now this something has two parts. The first one is the hyperparameter, which we select. So we tell it how much. How do you pronounce this hyperparameter here? I don't remember. Is it lambda? This isn't lambda, right?
Alpha.
Alpha.
Oof, now we hard because I knew the other way around. Okay, so alpha will be alpha is a new hyperparameter that we pick, and whatever is in this black box depends on the ridge, on which one we're using, ridge, lasso, or elastic. Again, just a quick update. The cost function is no longer, we're adding stuff to the cost function. And consequently, we're going to add more stuff to the gradient up here. It's no longer just going to be this one. We'll add the extra terms to the gradient. So it will affect our theta 0 and theta 1. Does that make sense?
It does. Like the first term, the mean square error, that's like the sum of errors. And like we're trying to decrease that one. But this one is regularizing the weights that we are trying to, the parameters of our, so it's also what like a cost function of the weights, not our actual instances.
Yeah. Yes. And alpha, or regularization term, this is the equation for this one, for the ridge regression. Now you can pretty much see if we set alpha to 0, if we get alpha to 0, we get back our old one, our normal cost function. So the higher the alpha, the more penalty, the more you're penalizing the weight for what do you call it? For overfitting the model. No.
Chima,
Yeah.
I have a question. I don't understand where that alpha times that one, the half thing, where did that come from? Because he was just saying that our, so I can't understand that 1/2 part of this equation. He mentions the alpha, and he mentions also the other thing, but there's no like one, like, yeah, like right over there, if you in the second line, yeah, there.
Yeah.
So
1/2 is a scalar, right? It's just a number. Basically, it's just a number.
yeah, why did he put that in then?
Because usually, if you add this number right here, it makes calculating the gradient easier, right? Yeah. So when you're calculating the gradient, remember in this equation here, I'll just pull it up on my slide, it's easier. Remember in this equation here, remember this is the gradient of the cost function with respect to theta, right?
Yeah, that's like the derivative of that, yeah.
Exactly. So when we're finding the derivative of that term, we would actually bring, where am I? Let me see. I went too far. We'll bring this 2 down here to calculate the gradient.
Yeah, but this is not the gradient though.
Yeah, but when we're bringing this 2 down here, right? Half times 2 will give you 1. So that's just sort of like to get rid of this, the extra 2 that's going to come down when we're calculating the gradient.
Okay, so basically we're just anticipating something later on calculation. All right.
Because when you calculate the gradient of this, when you calculate this, the gradient of this entire thing, which you will later, I don't think he does that. I don't think he does that either. No, he doesn't.
So it depends on if you want to do the, if you're, so he's using gradient descent for this one anyway, but I see what you mean. So it's just basically he decides to like add a number there, but that number, okay. All right.
Mathematically, it wouldn't change anything. The minimum is still the minimum.
Yeah, sure.
Times, okay. 2 times the minimum just means 2 times minimum, 2 times everything else as well, including the minimum. So mathematically, it doesn't change anything, which is why he can do it. I think Toby had a similar question last time about that. That was pretty much the reason, like scaling it, like multiplying by half or multiplying by 2 doesn't change too much. Yeah. And then, yeah, he says you should note that this one is not biased. The bias term, as in our x0, is not usually recognized. We don't usually penalize that one, but the other ones we do. So with this equation, with ridge regression, we're just adding this one to it. With the next, yeah. Oh, this is where he tries to prove it. This is where he tries to do it. And then he uses the library again. With the next one, lasso regression, the value, everything else is still the same. We're still picking this one. The only thing that has changed is just sort of the formula we're using this time around. This one is, I think, a little meaner than the, I think it's a little, yeah, tends to completely eliminate the weights of the least important features. Basically, it penalizes the model very harshly, more harshly than the last one, than the other one that we looked at.
And then also he didn't add that number to this. He decided probably he's not going to use it.
Yeah. No, this one there is no exponent. Usually, whenever you have squared or cubed, then you can sort of do that. But this, well, yeah, good catch, good catch. That was a good catch. Yeah. I think he's just sort of showing.
So here, what's happening is that we're saying that our algorithm, when we're not using the batch gradient, when we're using the mini batch or the stochastic gradient, usually we use the stochastic gradient. Design is that it really has trouble finding the local minima, right? The global minima. And so, and especially when you have polynomial, if you are to draw a line connecting all those dots, then you could really think you're at the minimum, but you're not at the global minimum, the true minimum, you know? And so with this jumping up and down, you know, he shows what this regularization means, you know, why that using that is important, and encourages for anyone to use it. And but you know, this is why we're saying, look, we know that our gradient descent jumps around and will never converge. And to make it converge, you either have an early stopping when when you draw your learning curves and the validation curve starts to increase and diverge away from the training curve, or you use these types of regularization. And yeah, so essentially those are the two things where you use the full, the whole batch. This is why this is important.
And then one thing that I also wanted to add is that it's very important if we understand the concept of norm in vectors and how it's applied to machine learning. And we're talking about the L1 and L2 norms. The L1 norms is just the quickest distance between 1 and 2. And the L2 norm is, that's the L2 norm. And the L2 norm, which is called Manhattan norm, is something different. And if we understand those, ridge and lasso regression would make sense. And this plot, which I think is brilliant, will make a much more sense. And by the way, my version of book, this plot, my version of book is totally different, and I think he revised it.
Yeah, so I have the early version. I think I realized last week I have the early version of the. What happened? Oh, okay. Sorry.
I think we've beaten that shape. You just have to know that you can use scikit-learn to do that regression. When should you use regression? So we can move on.
Yeah. Did someone try to share their screen? I think it's.
I'm not.
Okay. Okay. And then he talks about the last one, elastic net, which is sort of like the bridgeway between the two of them, between lasso is ridge and ridge. Lasso is somewhat mean. I think ridge is the meaner one. So he's saying this one's somewhat like the in between between the two of them. Yeah. And once again, the formula slightly different. If you notice, he adds the 2 here, because when we do that, it should cancel it out. Does the 3 forms of regularization, do they make sense?
Yeah, and the elastic form is the elastic net is perfect. It does make perfect sense, and we have 2 hyperparameters. One is alpha and one is r. With alpha is just whatever we chose for the previous ones, the ridge and lasso, and r is basically us telling our model how much of lasso or ridge to use. If r is 0, basically we are canceling the ridge, and all we have is lasso. And if it was 1, all we had was the other way. So ridge or lasso. Basically, by playing with r, we can just define how much mixture of those we need.
exactly. Because you
Could you scroll up a little bit on the down? Keep scrolling, keep scrolling, keep scrolling, keep scrolling. Oh, there. Go back
okay.
in the chart. You're moving too fast. Go up and just want the two charts side by side.
Oh, this chart. Okay, okay.
No, 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 not this one. I don't know this one. Go up. That one.
Oh,
Right.
I see.
Yeah, so this is what shows you the changes of the learning rate, like the alpha, right? When you have alpha of the blue is just like a linear regression without regularization. So you can see it's just a straight line. And on the right chart, it's this curve, which is just trying to fit into as many things as we can. And then when you increase your learning rate so that alpha is equals to 1, it almost becomes a straight line. And so you want to get an in-between, between 0 and 0.1, where you're trying to get a better fit, the green dotted line, which is just explaining again how you use this regularization and why it came into this chapter for polynomial regression. Yeah. I think we can move on from the regularization.
Okay, and then just do early stopping. So early stopping is sort of like I like this one because it's I don't know why. I just feel like it's
Because it's beautiful feeling.
it's just like, okay, whenever we feel like it's learned enough, stop. Like just stop. That's where, and he uses this graph to sort of show it. So typically you'll stop. You basically run it for some samples, right? Why did he do that? For some prediction. So you basically try different, what do you call it? Different models. And then you basically stop once you have a good value of theta 0 and theta 1. And I think this somewhat summarizes it. Sort of like a beautiful free lunch. Where like, okay, rather than keep training after you get to this point, I think dotted line is the desired error. So once we get close enough to that desired error, just stop. And typically, this is what you get. Does that make sense? It's just sort of like,
And so what you'll do here is that every time you train, you're going to save your model at every run, every epoch, and then you're going to plot your errors so that if you figure out, oh, my validation errors are increasing, so they're already at the minimum, then you'll have to figure out what was the minimum and then use those as your optimum parameters. Okay? That's the relevance of this, but yeah, I don't know that there's anything much more here.
And then we are using the whole data set to do this?
No, because it's stochastic gradient descent, right? So we are not. So or mini batches or whatever you want. But
so it's not the full batch then?
Usually not.
Okay, makes sense.
And this is where he implements it. Like Judy said, you just sort of save all your values. And once you just pick the one that gives you the smallest, or like the one closest to the desired, what do you call it? To the desired value, to the desired error. So to that, we come to the end of the first big one, which is linear regression on a whole. So overall, we've covered one linear regression, one value, how to solve linear regression using normal equation and gradient descent. And then we also did some problems with that. Then we also talked about the forms of gradient descent. And then lastly, the two other problems that it can have, overfitting and underfitting. With these, does it make sense so far?
Yes.
Yep.
Nice. So that's for gradient descent. The next one is logistic regression. Now with logistic regression, with linear regression, we're predicting one value. we're trying to say, okay, this is actually what happens. But with logistic regression, we're trying to predict the probability of something belonging to a class. So one very nice example, or one very simple example, is sort of like if you have an email, or like I do, or if I receive a phone call, is this a scam or not a scam, right? And basically with logistic regression, I'm trying to predict, okay, what's the likelihood that this is a scam? What's the likelihood that this is not a scam, right? Again, we'll talk about the hypothesis. The hypothesis is not too different. If you remember, this is the same thing. We had this x theta value, x theta value as we did before in linear regression. The only difference is we applied the sigmoid function here. This one, something we call the sigmoid function. And this is how you get the sigmoid function. Now, what that does, what the sigmoid function is, right? Since we represent, if it's a scam, if the phone call I'm receiving is a scam, then you say 1. If it's not a scam, then you say 0. What the sigmoid function does is it says, okay, using those values of x, using those hypothesis values, using the values you get, put them in between sort of like a range, represent the probability between 0 and 1. Does that make sense?
It does.
Yeah.
Yeah.
In between 0 and 1. And one very common metric is like, if the probability that we get, like let's say the probability that a phone call is a scam is 0.3, oh, then it's probably not a scam. If the probability that it's a scam is 0.6 or anything higher, then yeah, that's a scam. That's a scam.
Yeah, we're feeding our sigma function with our prediction, and
Yes.
as you said.
Exactly. Rather than just output one of the random values for linear regression. In logistic regression, it's between 0 and 1. Why is it between 0 and 1? Because of this function. Because of that last function that we applied here. Yes. And this one also has its own cost function right here. So the cost function is this. Basically, what this cost function is trying to say is, okay, in the case that I predict 1, right? And in the case where I say, okay, the phone call is a scam, but it's not a scam, the cost function should say, you're very wrong, right? It should be very large, correct? So in the case where my prediction, PI is my prediction. In the case where my prediction, where did he talk about that one? Yes, because this is very important. Minus log t goes very large as t approaches 0.
Maybe one thing that can help is that if we know that a logarithm of 1 is 0 and logarithm of 0 is infinite,
yeah.
And then that will explain why if we have a wrong prediction, and put that one in logarithms, then we will like how it will affect our cost function.
Yeah, so I see what you mean. That was what I was looking for. I was looking for the logarithm of 0 is 1 and logarithm of 1 is infinity.
Yeah, the logarithm of 0 is infinity. Logarithm of 1 is 0.
Yeah, my bad. Logarithm of 1 is 0. Logarithm of 0
infinity.
is infinity. Yes, that was the part I mixed up. Okay. Okay. So if I say, if the predicted value, if the actual value is 1, let's say the actual value is 1, and I say it's 0. I say it's 0. Then we get a logarithm of 1, which is 0. Right?
Yeah.
Yeah.
Yes, on the previous one, the 1 is actually, the 0 is actually giving you infinite, so it will increase your cost function anyway.
Yeah. Wait, I'm sorry, come again. You said if I get a 0.
So if this is so for example, if this is y is 1, it's supposed to be 1, meaning that if it's supposed to be 1, but our prediction is 0, the logarithm of 0 is infinite. So in that first part, it's gonna be it's gonna go high up, and it doesn't matter the second portion of the equation. Doesn't matter. It's already infinite. But it's on the other hand, if y is 0, the first portion is 0 to begin with, and the second portion, now we're using that 1 minus the prediction, the probability to help us get into the same.
To help us get into the same. I see what you mean. Yeah. I got in my head. I got mixed up with the log 0 and log 1. That's the pretty much the goal of a cost function, any cost function we use, is such that it tells you when you're far off, and just like that's the whole point of the cost function. Just like Elmira said.
Yeah, and I really like that this is like basically the smartest way of using the mathematical rules that we have to like create. So I think this is a very creative way of defining a cost function. I like it.
Oh yeah. Does the cost function make sense to everyone? Yes. And unlike now, he brings up a point here. It's like unlike linear regression, we can't do like normal equation and get it completely, but we can use gradient descent, the same type of thing that we do. The only thing that changes right now is, where's my equation for gradient descent? The main thing that changes, so this entire step stays the same. The only thing that has changed right now is this. Instead of that, we're going to use this, since we have a different cost function. In general, they usually represent cost functions as J. I do not know why. But in just traditional, if you're reading anything, they'll typically represent cost function as J. And that is what changes here. Does this portion, okay, up to here, before I start talking about decision boundary, does anyone have any questions?
So basically, when we are getting the derivative of a cost function, it's basically we're applying gradient descent on it as an equation 418. Yeah.
Once you have your cost function, to do gradient descent, you do your partial derivatives, you do your derivatives on it. Yes.
Sorry, Toby, I interrupted you.
Yes, so I wanted to add that, please can you scroll up? So this logistic regression cost function is like saying predicted minus what you actually got. So all these brackets in front here, that looks like it's confusing. So if you just open the bracket, you'd see that the left-hand side is what we actually have, and the right-hand side is what was predicted. So that's like the same way with gradient descent cost function too. So that's only what I have to.
The y is the actual number, the p is the prediction probability.
Yeah. Now, I don't know why he started this one. I don't know. I had a problem fitting this one in. I didn't quite get why he started talking about decision boundaries.
Yeah, I think it's just random. So he just puts.
It felt random.
No, exactly. No, I agree.
It wasn't just me. Okay, because I felt like he went random, like decision boundary. Let me see. Okay, it's just decision boundary and then softmax regression. Nice. Which was why I felt like when I was making the slide, it felt too specific. So I just said, let me use this one instead. So he uses this iris data set, which is a very popular data set in ML. And basically we're trying to that contains the width of 3 types of flowers. Iris, I don't know too much about flowers. I only get roses. And these ones. And then what he says is he's trying to build a classifier to detect the Iris Virginia type base only petals. So he loads the data, does that. They load the data and they do that. And then they make the model. Judy, do you have, I didn't quite, okay, this was the one I did. This portion, did anyone understand these, like why he was doing this portion?
So essentially what he's saying is that if you look at the boundary, keep following it, you'll see based on the petal width and the probability where you're scrolling from, that this Virginica usually starts from around 1.4-ish, but there's a little bit of an overlap, but around 1.6, it can tell you beyond this with 100%, right? Because classes, you're gonna distinguish them by using probability. So you're saying above this centimeters, I can tell you 100% that this is this type of flower. When you go down, the decision boundaries is what he tries to plot. And if you look at 0.75, 0.15, 0.60, it's more of like 75% of the time, I can tell you this is this flower. 190% of the time, I'll tell you that this is the flower versus going lower. So he was just trying to emphasize that, that sometimes, like the way you're making the decision on what class you want to predict, and this is a single class, then the probability and you'll hear most of the time when you're presenting this, we'll say what's the confidence interval so that we know what's included, right?
I see, yeah.
That's it. And then, so the softmax regression, all you need to know is that whatever is output by the model, it needs to be converted into a probability for it to make sense for a class. And so that's all you need to know. And you just need to know how it's done in scikit-learn. And then if you keep scrolling down, what he does is that he does this, previously we had just done 2 classes, right? 2 classes for the class prediction. So he shows you how to do a multi-class prediction here, which shows you the boundary spaces between all the 3 types of flowers that are in this data set.
Right.
Yeah. So I think, I think you've done a good job going through everything. I just wonder if people want to spend like maybe 5 minutes. It's a lot. It's a big chapter. If you guys want to spend 5 minutes to just go through the questions.
Yes.
Yeah. So the first one, and there are answers too, but what linear regression algorithm can you use if you have a training on millions of features? So basically, you should be using something with stochastic gradient descent, because if you have to load like a full batch or use the normal equation, it's going to be too heavy to do. And then, scaling. If it's a linear algorithm, usually it doesn't matter. But as you go with the other, I think, could you open the answers? Anyway, you should look through the appendix. But these questions can really help you solidify this answer.
This one, I think he was talking about gradient descent. Normal gradient descent does not suffer from scaling, because it's just math. That complex formula doesn't really suffer, but gradient descent suffers a lot from feature scaling. Next one, can gradient descent get stuck at a local minimum when training a logistic regression model? I think the answer is no. Let me check.
I thought it was yes, that the curve, the cost function that he introduced.
Yeah, let me try and get the answers.
Since the gradient descent is like a straight line and the logistic is like a convex curve.
Yeah.
So it gets stuck
We get stuck in
at the local minimum sometimes before reaching the global minimum.
let's see. The gradient descent algorithms lead to the same model, provided you let them run long enough.
It depends, right? So the full one will converge. It just takes a long time. But the mini batch and the stochastic gradient, you have to help it either by early stopping or doing something, you know. And then, suppose you use batch gradient descent and you plot the validation error at every epoch. You notice that the validation error consistently goes up. What goes on? So you're either choosing a big learning rate, so you're jumping from, you're not learning, coming down the hill very regularly, or you're overfitting the data. So you need to have early stopping. So you either need to adjust your learning rate, have early stopping, or add more data. And then and that's actually for underfitting, not overfitting. Overfitting, adding more data will not help. Like adding more test exams is not going to help. And then
Is it a good idea to stop mini batch immediately when no? What? No.
I think you have to, you let it go on a little bit, save your data, ensure that it's correctly going up. And then which gradient will reach the vicinity of the optimum solution the fastest? That's usually the stochastic gradient, but it never converges. So that's why you have to do the techniques to make it stop. And if you're using, you notice a large gap, I think you showed this uh, uh, on your chart. If you have a large gap or you have a small gap of errors, and then you want to use a rich regression usually, and then this class number 11, which is classify those 4 classes. They're interdependent, and as long as you so like an outdoor class, picture can also be in the nighttime or daytime. So you should build multiple logistic regression and notice a polynomial. You shouldn't use one softmax. So that's just emphasizing that softmax, the classes cannot be dependent. So you cannot use it to identify a program where multiple people have the same face. Like identify Judy's pictures in the library, but you can use between maybe cat and dog because those are two not independent classes. So I mean, this is a very very. It was a very bulky chapter. We took 2 times to look through it. What I would say is that just go back and just reflect on some of the things you've done. I think for quite half of the people on this call, we just need to know that this is how I implement it. And what I've been doing is that shortening my code. Like I'll never use normal equation. I just need to know that it's there, but remove it and just say, this is the code to do this on scikit-learn. And so I'm making my Google Color, but I'm not able to show it right now. But you can see it's cleaner so that if I get such a thing and I've forgotten what to do, I can go back and have the template already in place, okay? So I think, we'll hear some feedback from everyone else, and then we'll see who's going to do the next one, support vector, SVM support. Yeah. Toby, what did you think?
Yeah, from my end, yes, I did. I learned a lot, and it was a very interesting chapter.
Okay, Elmira.
I really like the chapter and I learned a lot. And one thing that I want to answer Chima about that decision boundaries, I just realized that it actually makes sense to introduce the concept of decision boundaries under logistic regression, because that wouldn't have made sense with linear regression. So that's why he's just introducing that under logistic regression. But I love the chapter.
Okay, Jeffrey, how was your fast? This was probably not the best chapter to come on. It was very hard. We spent 2 weekends going through it. But did you learn anything or?
Yeah, I did. I appreciate Chima. You did a really good job of explaining it. I mean, I know it's a lot of it is over my head, and I'm kind of being caught in the middle here. But I do want to like go back and go through it more thoroughly for myself. I may have more questions next week or in the interim, but I know I really do appreciate you going through everything, and some of the models do make sense, but there are some basics that I think that I still need to sort of go through.
Sen, are you still with us? Haven't given up?
I'm still here. You're waiting for me to give up, aren't you? That was great. I think Chima did a great job. I miss his creative OneNote presentation, but this one was phenomenal. I think he broke down everything really well. It was just really impressive. The chapter was pretty cool to kind of, because I always hated how he would just whip out, and not you, Chima, I mean the author, would whip out, okay, this is the function, it just does it for us. It was cool to see how it works. But yeah, it was pretty cool.
Did you learn anything? Okay, Chima, what did you think?
I think this was a good chapter. One thing I did realize was when I took a step back and I was like, okay, let me see if I can try and because you realize some of the stuff was like he was just pulling some stuff out, and it wouldn't make sense unless you're like, I feel like if you're fairly new to it, it wouldn't really make sense. But I definitely have a newfound appreciation for some of the models and how we implemented them.
Could you please post your slides on the Slack channel?
Yeah.
I thought they were a great way to summarize things. And okay, so I'm happy to do the support vector machines next week unless we have a volunteer. Elmira, do you have time to do that one, or do you want me to do it? Okay, I'll bring the next one so that I can show people a little bit and maybe go back through the previous weeks, make sure that we are all on track. I really encourage you. When I started to do machine learning, I had to set up everything, but now we can use Google Colab and all these resources. So next week I'm going to go through SVM and also introduce some other resources that can be supplemental reading. Remember, you have to practice either by doing a Kaggle challenge, but now we are increasing our base. So, even during the Monday discussions in the lab, things should start to make sense. You're like, oh, I know what they're trying to say or what they were doing here. And that's really what I want to do, to bring a good base for us to be able to either build machine learning models or work with other people who do. Okay?
Mm-hmm.
So thank you, everyone. Abby was on call today, and I'll see you guys next Saturday.
Thank
Thank
you.
you.
Thank you.
Bye.
Bye.
Thanks. Bye.